You know, linear programming is supposed to be this world of clear, predictable rules. You follow the steps, you get one perfect answer. It's all very neat. But what happens when the math breaks its own rules? Today, we're going to meet the 4 fascinating exceptions in linear programming, the cases where the models go a little bit rogue. So here's the game plan. First, we'll quickly set the stage with what a perfect solution looks like. Then, we'll meet our 4 troublemakers, problems with way too many answers, problems with no answers at all, some with infinite answers, and even ones with rules that just don't matter. And then, we'll tie it all together and see why these so-called errors are actually powerful business signals. All right, before we can really appreciate the rebels, we need to understand the establishment, right? So let's talk about what a perfectly well-behaved, by-the-book linear programming problem is supposed to look like. In a normal, everyday linear program, we expect 2 key things. First, there's one and only one best answer. Second, all the possible solutions live inside this neat, closed-off area called the feasible region. You can think of it like a fenced-in yard. All the valid answers are inside the fence. It's contained, predictable, and tidy.
And the process is just as methodical. You start by laying down the ground rules, like you can't produce -5 chairs. That's your non-negativity constraint. Then you add your limits, your budget, your time, your materials. You find the spot where all these rules overlap, you check the corners of that area, and one of them's going to be your winner. Simple, right? Well, let's meet our first rule breaker.
And this brings us to our very first exception, the case of multiple optimal solutions. This is where that whole simple idea of finding the one best answer gets thrown right out the window. The whole thing really hinges on this one question. So you have your isoprofit line. Just think of it as your goal line. You're sliding it across your graph, trying to find the highest point it can touch in your feasible region. Normally, it just kisses one single corner. But what happens if that goal line runs perfectly parallel to one of the boundary lines of your region? You get this. Instead of just one point of contact, the whole goal line lays perfectly flat against an entire edge of your feasible region. And what this means is that not just one, but every single point along that line is an optimal solution. Suddenly, you've got an infinite number of best answers. And hey, the numbers prove it. Our goal, our objective function, is to maximize this formula. Z equals 3 times x1 plus 2 times x2. So look at point B. We plug in its coordinates, we get a result of 12. Now look at a totally different point, point C. We plug in its coordinates, and we get the exact same optimal value of 12. That means both points are equally best, and so is every single point on the line connecting them. This isn't a glitch, it's a gift. It's called flexibility. So, we just went from having infinite best answers, and now we're going to swing to the complete opposite extreme. What happens when there are no answers at all? This is our second rule breaker, infeasibility. Infeasibility is what happens when your rules are at war with each other. You've set up a bunch of constraints that are so contradictory, it is mathematically impossible to satisfy all of them at the same time. There is no common ground, and because of that, there's no solution. Period. I love this quote from our source material because it just makes the concept so clear. It's like 2 people are giving you opposite directions. One rule tells you the answer has to be less than 4, but another rule demands it has to be greater than 8. Well, they can't both be right. They just go their separate ways. And when you graph it, this is what it looks like. Instead of one nice overlapping feasible area, you get these separate, disjointed regions that never touch. And since no single point can be in 2 places at once, there is no point in the universe that can satisfy all the rules. The problem is literally impossible to solve as it's stated. Okay, this next one is my personal favorite. It's the one where the model seems to promise you the world, literally. Welcome to our third rule breaker, unboundedness, where the solution just goes on and on forever. So, an unbounded problem happens when your feasible region isn't a closed shape. It's open on one side and it stretches out to infinity. This means if you're trying to maximize something like profit, there's no ceiling. You can just keep going and going and going, making more and more forever. Now, here's the crucial point. As amazing as infinite profit sounds, it's not real. Unboundedness is not you hitting the jackpot. It's a giant red flag. It's telling you your model is broken, you've forgotten a constraint, or you haven't factored in a real-world limit. It's a sign that you need to go back and fix your assumptions. This slide is great because it perfectly contrasts those two impossible scenarios. On the left, you've got invisibility. That's impossible because the rules clash and fight each other, leaving you with no solution. Then, on the right, you've got unboundedness. That's impossible because the rules are too loose, giving you an infinite solution. One has too many restrictive rules, the other simply doesn't have enough. Our final rule breaker is the most subtle of the bunch. It's not about having too many answers or no answers. It's about having a rule that does absolutely nothing. This is redundancy. A redundance constraint is just a rule that's already covered by another, stricter rule. Imagine you have a constraint that says x must be less than 10, and then you have another one that says x must be less than 12. Well, if you're already staying below 10, you're automatically below 12. That second rule doesn't add any new information and has zero impact on your final answer. And this is the perfect way to think about it. If traffic and stoplights already guarantee no one can go faster than 50, putting up a 100-mile-per-hour speed limit sign changes absolutely nothing. Yeah, it's technically a rule, but it's completely irrelevant to what's actually happening. You could remove it, and the outcome would be exactly the same. So we've met the 4 rule breakers, but these aren't just quirky math problems. In the real world of business and planning, they are incredibly important signals. Let's just quickly recap what these signals really mean. Multiple solutions? That gives you strategic flexibility. Infeasibility? That signals a fundamental conflict in your goals. Unboundedness? That points to a major flaw in your model's logic. And redundancy? That just reveals an inefficient or useless rule in your system. And this is the real takeaway. When your LP model gives you an error, it's often not a math error, it's a business error. Infeasibility might mean that the production department's goals are mathematically impossible to achieve with the marketing department's budget. Unboundedness might mean you forgot to model market demand. These are not glitches, they're diagnostics. Okay, time for a quick quiz. Look at these constraints. One says the sum of x1 and x2 has to be greater than or equal to 8. The other one says the sum has to be less than or equal to 4. What kind of problem is this? It's infeasibility. The rules are in direct conflict. There's no number in the world that is simultaneously bigger than 8 and smaller than 4. So we'll end on this thought. The next time a mathematical model gives you an impossible or just a strange result, don't just see it as a mistake you need to fix. Ask yourself if it's actually a hidden, valuable insight. Is the math telling you something fundamental about your strategy that everyone else has missed?